categorize into your primary lymphoid organs and then your secondary lymphoid organs. The primary lymphoid organs, also known as the central lymphoid organs, are the organs where the lymphocytes, like your B and T cells, are generated and eventually become mature. These organs provide an environment for lymphocyte development and selection, ensuring immunocompetence and self-tolerance. The secondary or peripheral lymphoid organs are sites where antigen encounter, activation, and clonal expansion of mature lymphocytes end up occurring. These are ultimately structured to optimize interactions between antigen-presenting cells, the antigens, and in the lymphocytes. So let's explore the specific primary lymphoid organs. The first one is bone marrow. The function of the bone marrow is to initiate hematopoiesis, which is the production of all blood cells, including your lymphoid lineages, like the B cells and the T cell progenitors. I should clarify that I meant to say the B cell progenitors and the T cell progenitors. It is also the site of B cell development and maturation, particularly in humans and mice. Regarding its histology, a bone marrow can be identified through the presence of the reticular connective tissue stroma and the arrangement of hematopoietic cells around the sinusoids or vascular spaces. The figure over here on the right is one example of a histological tissue sample of the bone marrow, where we can see the presence of megakaryocytes and granulocytes, along with a bunch of erythroid islands and the presence of sinusoids, where the cells are arranged around them. Some key processes of the bone marrow are B cell maturation, and that involves the somatic recombination of immunoglobulin genes. There's also the expression of pre-B cell receptor, also known as pre-BCR, and then there's negative selection. There's also central tolerance, which is a deletion of autoreactive B cells. There's some clinical correlation to keep in mind, such as aplastic anemia, leukemias, and multiple myeloma, because they involve this organ or the bone marrow being affected. Now let's talk about the thymus. So the function of the thymus is to initiate T cell development and maturation. The way I remember that is that thymus begins with the letter T, and T cell contains the letter T. So that can help you to remember that T cell development and maturation occurs in the thymus, while B cell development and maturation occurs in the bone marrow, because bone marrow contains the letter B, and then B cell also has the letter B. Regarding the anatomy of the thymus, it is basically a bilobed organ located in the anterior superior mediastinum. It tends to be the largest during childhood, but involutes after puberty. The figure over here shows a general location of the thymus within the mediastinum. Notice how it is located anterior to where the trachea would be, along with the bronchi. shows a histological tissue sample of the thymus, and we can see the cortex surrounding the medulla. So what is the medulla? Well, the medulla contains fewer thymocytes, and it contains what is called Hassel's corpuscles. The Hassel's corpuscles are keratinized epithelial structures with unclear function, but they may induce regulatory T cells. And we can see the medulla here being surrounded by the cortex. And then the dark purple color of the cortex is due to the high concentration of lymphocytes in the cortex. And this time, the concentration of immature T cells. So what are the key processes in the thymus? There is positive selection that occurs in the cortex. This involves the selection of thymocytes or immature T cells, selecting them that recognize the self-matrix histocompatibility complex. The negative selection occurs in the medulla. This involves the deletion of thymocytes with high affinity for self-antigens. This results in self-matrix histocompatibility restricted and self-tolerant naive T cells. Some clinical correlation to think about include the George syndrome, which involves thymic aplasia, or the lack of growth of the thymus, which is obviously going to result in T cell deficiency. And then the thymomas are known to be associated with myasthenia gravis, or pure red cell aplasia. Now let's talk about the secondary lymphoid organs. So, unlike the primary lymphoid organs, the secondary lymphoid organs organize the lymphocyte encounters with the antigens and allow for the generation of adaptive immune response. That's the key word, adaptive immune response. So the first secondary lymphoid organ we have are the lymph nodes. The function of the lymph nodes is to filter lymph or the lymph fluid before it gets drained to your venous blood system. It is also the site of antigen presentation to your naive T and B cells that were developed and matured in your thymus and bone marrow, respectively. And this leads to the initiation of adaptive responses. Regarding the anatomy, the lymph nodes are basically distributed along the lymphatic vessels, as shown over here. They are also encapsulated, and they consist of afferent and efferent lymphatics. So we can see all these different lymph nodes located across your body, like the axillary lymph nodes, the cervical lymph nodes, pelvic lymph nodes. Just be aware of all these different lymph nodes. Regarding the histology of the lymph nodes, the cortex is also known as the B cell zone. This is the primary and secondary follicles with terminal centered you see a tissue sample like this, think about lymph nodes. So there are some key processes associated with lymph nodes. First, we have germinal center reactions, where class switching, somatic hypermutation, and affinity maturation occur. We also have memory and plasma cell generation occurring in the lymph nodes. And then some important clinical concepts to think about are lymphadenopathy and infections and cancers, and lymphomas that can arise from the germinal centers, like follicular lymphoma, for instance. So once again, this is where the germinal centers will be found. Alright, the next organ that we have is the spleen. The spleen functions as a filter for the blood-borne antigens instead of the lymph. It also clears old red blood cells, and that's the function of the red pulp of the spleen. On the other hand, the white pulp that we see over here that look like blueberries, they're in charge of immune surveillance for blood pathogens. Regarding the anatomy of the spleen, it is located in the left upper quadrant of the abdominal region, and because of its function with filtering blood-borne antigens and clearing old red blood cells, it is highly vascularized. If we go back to the image over here, this is where the spleen would generally be located. You can see this is the left upper quadrant of the abdomen, while this is the right upper quadrant, right lower quadrant, and left lower quadrant. Let's talk about the histology. So the white pulp of the spleen, as they look like blueberries over here, they have periarteriolar lymphoid sheath, and they're rich in T cells. They also have follicles, which have B cells. The red pulp consists of cores of bilirubin, sinusoids, and macrophages. And you can also see some arterioles, some arteries, and the trabecula, and some clinical correlations to think about are number one, asplenia, which can occur due to post-splenectomy or the removal of the spleen. It can also occur due to sickle cell disease. With asplenia, there is increased risk of infection by encapsulated organisms, such as your Streptococcus pneumoniae, Asian influenzae, and meningitis. So just be aware of that. With asplenia, we need to think about increased risk of infection by any encapsulated organisms, especially these pathogens listed here. Also, when you do a blood smear test and you see L-jolly bodies, that can indicate the occurrence of hyposplenism. And with a blood smear test, the L-jolly bodies will typically look like this. So be on the lookout for them, especially when you suspect a patient having hyposplenism. Okay, let's move on to the mucosa-associated lymphoid tissue, also known as MALT. So the mucosa-associated lymphoid tissue can also include GALT, or gut-associated lymphoid tissues, BALT, or bronchial-associated lymphoid tissue, or NALT, or nasal-associated lymphoid tissues. They can also include tonsils, appendix, and Peyer's patches in the ileum of the small intestine. Overall, the functions of these tissues is to protect see over here, along with specialized epithelial structures such as the M cells and the Byers patches that are needed for antigen sampling. However, that is not shown over here. Some key cells with these tissues include the secretory immunoglobulin A producing plasma cells, and then regulatory T cells like Th17 cells. These cells are particularly found in the gut-associated lymphoid tissue. Lastly, some clinical correlates to think about include immunoglobulin A deficiency, inflammatory bowel disease, the mucosa-associated lymphoid tissue lymphoma. Interestingly, this is associated with H. pylori infection. And then, to conclude, we have some tertiary lymphoid structures, which are neither primary or secondary. And so, we have ectopic lymphoid aggregates that can form in cases of chronic inflammation, such as autoimmune disease or cancer. These are not present under normal physiology. Sometimes they can mimic features of the secondary lymphoid organs, and then they can be sites of ectopic antigen presentation, which means it can be implicated in diseases like rheumatoid arthritis, Sjogren's syndrome, and chronic infections. So, I made a summary table for you all to reference where you can compare the primary organs and the secondary organs. Remember that the primary organs are responsible for lymphocyte development and maturation, while the secondary organs are responsible for immune activation and antigen presentation. Primary organs include the bone marrow and the thymus, while the secondary organs include the lymph nodes, spleen, and the mucosa-associated lymphoid tissues. And be sure to know all these other details. Well, that is it for today's video. I hope you enjoyed this ASMR style